Good afternoon, everyone. I'm Karthik, Assistant Professor, Mechanic Engineering Department from SNS College of Technology. Uh, in last videos, we have seen about two case studies, one due to fatigue and another due to creep. Here, this case study is completely about the failure analysis of the weld flange, right? Okay. Before going into the case study, we have to see one thing. First one is that the history behind or the history or the scenario when this particular failure happens. First, it in January 1988, it is happens at Belgium. So here the component with the coarse grained microstructure was installed in a high density polyethylene loop reactor. Okay, so the coarse grains here the coarse grains come to the picture, as I already said in one of the video that in coarse grains the strength will be much lesser compared to fine grains, right? So here the dimension is that the next one is dimension is face 101 mm thick, 24-inch, and the material is ASTM A105 carbon steel. In this, the first figure, it sees about the flange cracked at the transition between the conical and the cylindrical part of the weld neck. That is here in this here in this part. The second is that location that coincides the cold area. Here this okay. This is the figure one. We can see here the temperature distribution is uneven. One side it is minus 16 degrees Celsius and on the other side it is plus 60 degrees Celsius. So there is a vast difference between the at a mass difference of temperature, or in other ways you can see it's a uneven distribution of heat or uneven temperature distribution in this whole flange. Right, here this is the crack that is formed in the flange area. The next one is that in the metallography study we can see that in original 24-inch flange from that high density polyethylene reactor has not been normalized correctly. Normalized means that here the normalization is nothing but when you're while heating the particular component, here after heating the component we have to hold the component for a particular temperature inside the furnace, but at the cooling stage we have to take the component outside the furnace. So it takes or here the cooling of a particular component takes place in a rapid manner when compared to tunneling, which you have previously spoken about, or we have videos previously about tunneling. Here this normalizing is that we have to heat that particular component inside the furnace, hold the component inside the furnace, and we have to while cooling we have to cool in the open air. So here due to this unbalanced or uneven normalizing, we can see coarse grains microstructure has formed. So compared to tunneling, in normalizing we should have fine grain, because fine grain structures, fine grain microstructure have high strength, but in a coarse grained microstructure you can see there is a decrease in strength when compared to fine grained microstructure. So here the difference between the maximum and minimum grain size will deals about 1,3 and 2,3, or in other ways in another manner we can say 1.3 to 2.3. So this difference in ASTM grain size can easily say that it is a coarse grained microstructure. This coarse grained microstructure will always leads to the depletion of strength of a particular material. So here you can see this is a coarse grain structure. In a magnified view we can see we can see the we can see due to this uneven normalizing we can see the fine grained microstructures are formed, and this white colors are nothing but the ferrite structure, and this is carbide region, right? So this is an elaborated region. Some small hydrogen cracks are formed at the polyethylene in the weld area. You can see this is the enlarged view. You can see the cracks here, right? So when we take a chemical composition, we see the predominantly we can see silicon, which is 0.1 to 0.35, and manganese is 0.6 to 1.05 percentage weight percentage is formed, and this chemical composition is perfectly okay and matches with the condition. The next thing is that in mechanical testing you can say the transient temperature corresponding to such these flanges is as a with the impact toughness of 27 joules at about 10 to 10 sorry about 20 plus 20 degrees Celsius. At a minimum operating temperature is allowed is minus 29 degrees Celsius allowed by ASME B331.3, but these flanges are possessed toughness less than 10 joules. So this is mainly due to the mainly due to the microstructure, coarse grain microstructure. Okay, so as from the metallurgical examination, it is concluded that 40% of the flanges which are investigated has not treated properly, which means it's not heated properly for after forging, despite that accompanying certification that flanges has been normalized. But this investigation proves that many of the flanges are not investigated or are not what are not normalized evenly. So there may be formation of coarse grain structure, which leads to the decrease in the impurities material properties. In the next evidence, it says that this coarse grained microstructures are nothing but the presence of Wittmann-Statten ferrite. This Wittmann-Statten ferrite or the coarse grain structures will perfectly helps to reduce the mechanical properties. Okay, the final is that as this carbon equivalent of this flanges range from 0.36 to 0.47, which is high. So sometimes this carbon equivalent in the flanges is also reason for the failure, and it is indicated at the certificates before installation, right? And the next thing is that it is concluded that the first information report says that data and certificate do not comply on the test results. So there may be variations in the data that is collected and the results, and also that the heat treatment, that is normalization, is not performed properly. So this results in very large grain size and poor toughness. So the larger grain sizes will always leads to poor toughness. So the next thing is that present investigation is that on this variation temperature from minus 10 degree to minus 29 degree, it should be 8.6 or 9.4 the appropriate toughness, but it is not present there. And it is recommended to perform ultrasonic as well as the other testings before putting the particular flange into the service again. Okay, so this is the case study. This is due to flanges that is done due to the welding part. Okay, thank you.